Speaking of making your life easier, this next section makes your life a ton easier, makes a lot of mathematics way easier. It's called orthogonality. Did you guys talk about orthogonality? Maybe? How many people took linear algebra? Okay, that's probably where you heard it a lot. Maybe Calc 3? Yes. Yep, that's why I loved Calc 3. And everybody's like, that's exactly why I hated Calc 3. It just seemed like physics at that point to me, so I'm like, okay, I finally get it. I like it. I also quit going to metal shows like the nights before exams and did way better, it turns out, when you're not up till 4 in the morning. What? Oh, that's listening to us? Ah! Was that one interesting? So orthogonality comes up a lot in linear algebra. We're going to see it a ton in this class, and it looks scary. I'm going to ask you to prove it in some cases. But if you ever see orthogonal function from like here on out, you're going to be like, hell yeah, it's either 1 or 0. And that's the beauty of it. Okay. If two functions, we're going to call one psi sub I and psi sub j, are orthogonal. Then we can have two outcomes. D tau this is true for when I does not equal j. So if they are orthogonal and they're different functions, what's the result going to be? Yeah. If they are the same function, what's the result going to be? Yeah. That's great. If you throw an operator in here, though, it can change things up. We don't necessarily know if that's the case, but if you're told they're orthogonal and you ever see this anywhere, you can always say 0 or 1. But remember, like, operators always act on which direction, right? And the commutative property isn't always true in this type of mathematics. So, okay. So this makes derivations a million times easier. Especially when we get way later on. The big thing is an operator cannot be present inside the integral. Oh, inside integral. What happens if there is an operator in the integral? What do you got to do? So what do you need to do in that case?
Basically, you have to apply that.
Exactly. So you do the operator first, and then if things look okay, you can use this, and then your life's golden again. So if the operator is inside the integral of the operation, operation, I think is the best way to put it, must be evaluated before you can consider the integral zero or one. So like I said, it's really beneficial. If I don't ask you to prove this, and it says the functions are orthogonal, a lot of your math just goes away. Am I okay to erase this side? Let's look at an example. And we're going to look at a system that you guys are going to see a lot in the future, a one-dimensional particle in a box. So example demonstrates that for a 1D particle in a box, psi sub 1 is orthogonal to psi sub 2. And those wave functions, psi sub 1 would be equal to square root 2a times sine of 1 times pi x over a. Have you seen that somewhere before? Yeah, you're going to find a lot of these things nested in one another. What do you think psi of the first excited state, or principal quantum number of 2, what's that going to look like? The normalization constant doesn't change. Instead of it being sine of 1 pi, yeah. We'll derive that and where that thing comes from soon enough. Okay, what are we looking for? Or what do we need to do? Yeah, demonstrate orthogonality. What information do we need? Yeah, we're gonna need the complex conjugate of those functions, or at least one of them. Okay. If we do this right, we're gonna have an integral. What's that integral gonna be? Yep. We want to demonstrate that they are orthogonal to one another. So what should the value of this, oops, excuse me. There we go. What does that have to be equal to if they are orthogonal? Are they the same function? If they are the same function, what's the value of it? 1. So 0. I love having 2 answers. That's all you got to worry about. 1 or 0. Okay. So we got to show that that's true. Let's move over here. Okay. Integral psi 1 star, psi 2, dx. Integral, what's my range? I don't think I ever said that, did I? Based upon the last question, what range was this function okay across? From 0, yeah, to a. Again, we'll derive that later, and that's like the length of the box. What does that even mean? Don't worry about it right now. Just focus on the math. Okay, we got to take the complex conjugate of this guy. Anything change? Nope, it's nice, no eyes. X over a. And what do I need to integrate across? Yep. Okay, let's make this a bit simpler. What would you do to make it simpler? Yeah. That's the normalization constant. At least this square root of 2 over a. Then we got this integral. What's the rest of it going to be? Can we combine those two to make sine squared? No, we can't. So we get sine, oops, pi x over a get that guy. Anybody know or remember how to do that integral? You might be able to. Yep. I have no goddamn clue of how to do that. Integral table is how I'd operate. Yeah. Sub and stuff. Okay, if you look up the table of integrals, I'm going to write it down. Yeah, actually, I could probably fit it over here. Got sine of ax times sine of bx dx. If you integrate that, get sine of a minus b times x divided by 2 times a minus b plus sine a plus b x divided by 2a plus b. Thank you, whoever determined that. Okay, on your cheat sheets that you have, I will give you table of integrals. If I ever screw up and you get to something, let me know, and then I'll probably be like, well, this is what it is. Good luck. Okay, what's our A and what's our B for this thing? Yep. And I wish they picked a different symbol than A, or I picked a different symbol than A. What is my B equal to? Yeah. Okay, so we're going to have to sub some stuff in there. We get sine A minus B. Pi over A minus what? Yeah. And that's multiplied by what? Yeah. And then we got pi over a minus 2 pi over a. On the other side, that is times 2. Thank you. The other side, we just have an addition of the 2, right? And we're going to evaluate that from 0 to what? Yep. It's telling me to shut up. We're almost there. Okay. Let's just focus on these sine parts right now. Sine pi over a minus 2 pi over a times x. What's that going to simplify to? Yep. Okay, what about the other portion where we have the addition? Okay. Oops, I wanted to do. So let's plug in at our limits. And what's our upper limit? A. That's going to work out to be what? What's that equal to? Yep. What's sine of 0? Yep. Okay. What's sine of, what's that going to simplify to? Yep. What's that equal to? Everything that we plug in is going to be what? Yeah, because there's a factor of pi in here. Anything that's a factor of pi in regards to sine is 0, right? So this whole thing works out to be a 0. Are these functional, or excuse me, are these functions orthogonal to one another? Yeah. So on your daily problem, or at least one of them in the future, I'm going to ask you to prove if these things are orthogonal to one another. Or give you a different set of functions and say, are they orthogonal? Okay, are there any questions about that? Understand orthogonality, like when is it 1, when is it 0, because it will benefit us a ton later on. For this stuff, try to plug in the mathematics, check to see if it is 0, but really think about the value of those sines and cosine functions you're going to see a lot. Okay. Any other questions? All right.